Introduction. So I'm going to present a wireless passive pH sensor that's going to monitor the milk quality. So the motivation for this work was foodborne illness. Every year foodborne pathogens cause a lot of illness and hospitalization around the world, and a lot of this illness is so bad that it can cause death. And since milk is a widely consumed food product around the world, it is very important to monitor food quality during storage and transportation. So that was the motivation for our work to monitor the milk quality. So in my talk, first I'm going to talk about some current techniques that are used for milk quality monitoring. Then I'm going to talk about the wireless passive pH sensor that we are working on, and then show some experimental results. So bacteria growth is the major source that causes milk spoilage. So the most common technique that is used for milk quality monitoring is the standard plate count or cyclotropic bacteria count. Now the problem with these techniques are they are really time consuming and labor intensive. A less labor intensive technique is microbiological impedance measurement that counts bacteria too. But the problem with this is it's invasive. So every time you try to monitor the milk spoilage, you have a probability to get contamination from the outside world. And then there is another technique that you can use gas sensor to monitor milk spoilage, because during the milk spoilage process, there are a lot of gas byproducts. One of them is carbon dioxide. However, gas sensors are easily affected by environmental conditions such as moisture and temperature. So we wanted to use the fact that when the bacteria grows in milk, the pH changes because the bacteria turns the lactose in milk to lactic acid and drops down the milk pH. So using a wireless passive pH sensor, we wanted to monitor the milk pH and detect the spoilage. So the criteria for our sensor is we wanted it to be passive, so no battery or power source on the sensor side. So the advantage of that is once we embed the sensor inside the milk package, we don't have to take it out to replace the battery or recharge the battery on the sensor. So there is no chance of getting contamination from the outside world. And also we wanted it to be embeddable inside the milk package. That means we don't want the sensor to be influenced by the fluid medium surrounding it. And of course we wanted it to be simple in design, so it's low cost sensor. So that's the block diagram of our sensor. So you can see it's actually based on pH combination electrode potential measurement. So we have a pH combination electrode which is actually in contact with the contact solution or the milk, and this combination electrode is connected in parallel with a voltage dependent capacitor and a fixed inductor. So as the milk pH changes, the voltage across this combination electrode changes, which changing the capacitance and changing the resonant frequency of the sensor. And interrogator coil is inductively coupled to this sensor inductor and tracks the resonant frequency of the sensor. Now this is the sensor that we developed at the beginning. So it's the spiral inductor made on a PCB board, and then there is this sensing circuit that contains the voltage dependent capacitor and some other circuit, and this is the pH combination electrode. Now for the pH combination electrode, we choose iridium oxide sensing electrode and silver chloride reference electrode. Now there are other electrodes that you can use for pH sensing, but these electrodes are already used for a lot of biological pH sensing, so that's why we choose these two electrodes. Now one of the task to use the sensor in fluid medium was the encapsulation, because we don't want the circuit to be get shorted when we use in a fluid medium. So we encapsulated with a plexiglass sheet. So we sandwich the sensor between the two plexiglass sheet. However, you see we have a quite thick plexiglass sheet on both sides. Now the reason behind it is we wanted to reduce the parasitic coupling from the liquid medium. It's just not to save it from the liquid medium, because it's we are operating in the around 18 megahertz range, and when we use it in the fluid medium, we get a lot of parasitic coupling. So to reduce that, we had to use a thick layer of encapsulation. So this is the circuit diagram of the sensor, and so for the voltage dependent capacitor, we are basically using a varactor, and we have a low pass filter on the sensing circuit, so the varactor is only responsive to the DC voltage change of the combination electrode. And so the way we measure the resonant frequency is we monitor the input impedance across the interrogator coil, which is given by this equation, and then we take the real part of impedance, which looks like this blue curve, and wherever the real part of the impedance is the maximum, that corresponding frequency, we take it as the resonant frequency. Now, talking about the encapsulation thickness, if we have a very thin layer of encapsulation, then we get a lot of parasitic coupling, and that's how our response looks like. So the Q is very low, and so that doesn't give a very good resolution in our measurement. So in order to have a high Q and to reduce that parasitic coupling, we have to use that 6 millimeter thickness of encapsulation, and that's how the signal looks like with the 6 millimeter thick encapsulation, and our resonant frequency is almost equal to the resonant frequency when the sensor was in the air. So for the experiment, what we did is we mounted the sensor inside a standard milk packet, and we monitored the resonant frequency with an interrogator coil and an impedance analyzer over 3 days. So we just kept the milk outside for over 3 days in room temperature. And also at the same time, we had a commercial pH probe to monitor the pH. So the commercial pH probe was connected to a data logger. So in the left, you can see that's the impedance frequency response for two different milk pH. So you can see that in a fluid medium, we have a very good quality factor for our response. And this is the green curve is the pH measured by the commercial pH probe over the 3 days, and the blue curve is the resonant frequency of the sensor. So you can see that the resonant frequency changed almost the same way the pH of the commercial probe was changing. So then we plotted the resonant frequency versus the pH measured by the commercial pH probe, and we found that the relationship between them looks very linear. So from the linear fit, you can see we have almost like 100 kilohertz per pH sensitivity, and the maximum deviation from the linear fit was around 0.12 pH. So another important thing was for the sensor was the response time, because we wanted to monitor the milk quality in real time. So we found that the response time is not limited by the electronics of the circuit or the interrogator coil, but the response time of the combination electrode. So what we did is we put the combination electrode in a standard 4 buffer solution, and we added some base and did a step change of 1.6 pH and monitored the voltage across it. So we found that to have like a 0.1 pH accuracy in our measurement, we can reach that value within 1 second. So we can get a response time of 1 second if we want like 0.1 pH accuracy in our measurement. So in conclusion, the sensor could be embedded in a fluid medium. So it can be used for like monitoring milk pH. It can be also used for monitoring other liquid food products. And this pH measured by the sensor was in good agreement with the pH measured by the commercial pH probe. And with that 1 second response time, actually we can do like real time in fluid monitoring. And the sensor is very simple in design, so there is no custom IC in it, so it will be very cheap to produce. Now, one thing about the thickness of that encapsulation is 6 millimeter, and it's not very realistic to put that in inside a milk packet. So one way to reduce the encapsulation thickness is to reduce the sensor coil size. So we developed this small sensor. This coil is only 0.5. This coil is about 5 millimeter by 12 millimeter. So for this size of a sensor, we need only 0.5 millimeter of encapsulation thickness. So this is like really small in size, so this can be easily integrated in like small food package. We are actually using this sensor now to monitor pH inside small bioreactors, but this can be easily used for monitoring food quality. So that's the end of my presentation, and if you have any questions.